the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. At the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Thank you, Dr. Sarkar, and thank you all for coming here. So let me introduce a new type of environmental problem that we don't actually see here in New Jersey. But if you are familiar with one of those mining states, this is what you see in your everyday activity. So it's called acid mine drainage. It's very common with both active and abandoned mine sites. So it's a big time environmental problem. So this is the kind of outline of my talk. So I will introduce the topic. Then I will talk about the area, why it is very important to focus on, and what was the objective of the study. I will briefly discuss about the methods and results, and finish it with major findings. Before doing anything, let me ask you guys about one question. Do you have any idea what was the most recent AMD spill in the United States? It was all over the news last year. Any guess? All right, so this was the picture. So in August 6, 2015, in Colorado, one river named as Animas River. So people there wake up in the morning and saw their very, neighboring, river. This river was mostly used by agricultural use for drinking water purposes. They saw that it turned completely orangish, and they have no idea what was happening. So not very far from, now. It's only 1 year, a little bit more. So what happened, there was an abandoned mine named Gold King in Colorado. So US EPA got information there was some kind of leak going on. So they sent their crew to inspect it, what's happening. And instead of repairing that, they accidentally opened the channel and spilled 3 million gallons of AMD water into this river, which turned within hour the entire river into this state. So people usually use that river for recreation purpose, but that they saw it, it's gone. So what happened? So I will tell you how AMD is being generated, but let's see one spill, what impact it had at that time. So the states Colorado, New Mexico, and Utah, they were directly impacted because people were 45,000 people were directly using the river in some other ways, and EPA calculated the cost was $3 million. So one accidental spill cost them $3 million, and it's still, the remediation is still going on. So it's a long, in a very long range impact it can have. So now let's see what AMD is. AMD is a kind of highly acidic metal contaminated water. It usually generated from oxidation of pyrite. If you know about the mine site geology, pyrite is very common mineral there. If it exposed to air and oxygen and water, it can generate iron hydroxide, and that's the color. It's called yellow boy. Once it's generated, it can turn the entire surface water into that color, and extremely high acidity, like 2 to 4 in the range, so high acidic, so nothing can survive. So let's see, visualization is always good. so now imagine if there is AMD contamination, how this animal, the local biodiversity can, what kind of impact they have. So acidic, highly acidic solution with metal. So it can, wipe out the local biodiversity. And another problem is soil erosion. So if the soil is exposed to AMD, you can see it become very much erosion prone. So these are the main two, direct impact of AMD on environment. So because of the problem, AMD is often called as multi-headed beast, because once it's generated and once it open to environment, it can create an array of consequences, which is very hard to deal with. And mostly in US, there are a huge number of abandoned mines. On paper, it's more than 500,000, but remember, there are even more which are not even listed, because before USCP came into action, we don't even have to report this site. So we don't even know what's the actual number. But directly right now, 15,000 to 23,000 kilometers of streams in US is directly impacted by AMD pollution. We don't see them here, but states like Pennsylvania, West Virginia, this is very common. And the NFS, National Forest System, they estimated the cleanup can cost around $4 billion. So we are talking about a big environmental problem, which is very difficult to tackle with and very expensive. So there are remediation and remediation techniques available in market, like they can be preventive, like seal the mine site and contain it so it cannot come out. The same thing they did with Gold King mine, but over the years, if you don't maintain it, it can come out. Same thing happened with Animas River, right? There are some remediation techniques, both active and passive. You can add chemicals to neutralize the acidity and take up the metals, or you can build some wetlands, SRB, sulfate reducing bioreactors. But all of this, this kind of thing is happening in Colorado right now. So they prepare catchment basins. They're trying to contain the water, add lime to neutralize it. But this whole thing is very time consuming and expensive. But the problem with the conventional remediation technologies are, first of all, you need land, which is very expensive. Huge construction cost. Management, you have to do constant management and monitoring, and different type of maintenance, sludge handling, removal, because once you add some chemicals, there are some consequences for that too. So there are several disadvantages for the current AMD remediation technologies. So now let's see about our area of study. So it was also another abandoned mine site. It's named as Simcoe. It's located 6 miles southeast of Carbondale, Illinois. So what happened in 1890 to mid 1900? Because this was a very coal-rich area, right? So they did underground mining. So they removed first part. They removed the bottom layer. Then they removed the middle layer. And what they did, they sealed the entire mining area with water, and they left the underground mining company. So after few years, the surface mining started to happen. So they now started to remove the top layer. So what happened in due course is they crack open some portions, which was releasing those sealed underground mine water. And once it's open, oxygen is going into, so there is pyrite and water sitting there. It was sealed. Now you opened it, so now oxygen is penetrating, so it started forming AMD. So currently 40 to 70,000 cubic meter of AMD contaminated water is existing in that area. And because of this kind of streams, the seeps, they are continuously releasing into the surface. So this is this is the local picture. So I will briefly describe what they are, but the area looks like something like this, fully contaminated with AMD. So because of its problem, in 1996, Simcoe was declared as one of the highly contaminated AMD sites in mid-continent region. It was a big deal at that time, but currently still 150 cubic meter of AMD is being generated per day, and it's impacting the area continuously. So this is a Google Earth picture when first time I took it. So you can see this whole area is the kill zone. Because of the elevation, AMD is coming from those ship and it's flooding through its floodplain, and it's going, and there is a river which you cannot see here, and it's meeting that river. So entire this area is being impacted. So because of the toxicity, there is nothing can grow there, no plant or something. So that's why they called it as a kill zone. 7-acre kill zone existed there, and 2 miles of a river flowing just under this canopy is also impacted because of that. 2007, the Illinois Department of Environmental Protection and a local University of Illinois, they created a sulfate reducing bioreactor there. So first few years it worked, but nobody, because it was a government project, nobody maintained it, so it failed in 2011. And the entire area is kind of like holding basin for AMD water, because that's how they design. Whatever is going to come, they're going to contain in that SRB pond, and the idea was to remediate it, but once it stopped working, now it's full of AMD water. So you can see, so this is whole area is kind of a full storage of AMD. So and this is actually the sulfate, that SRB pond. So it's full of AMD water, nothing else. And this is the Sycamore Creek, the river that's flowing nearby. So because no biodiversity exists in those part of the river. So you can imagine how big environment impact is happening because of the AMD pollution there. So the water we tested, so the pH was around 2.27, highly acidic, and there was high amount of metals, mainly iron. The US EPA limit of iron for surface water is 1 ppm. We found 137 ppm of iron there, so more than 100 times. And there are other, all those metals in red here are more than US EPA, their permissible limit. There were arsenic, lead, zinc, cadmium, everything was there. Let's see about the soil condition. So this was the soil taken from that, picture taken from that area. The pH was same, 2.69, highly, full of iron, more than 40,000 mg per kilogram iron present in that soil, and with all other different type of metals too. So when we started this project, so the objective was clear. So develop a new type of innovative technology, because conventional technology already failed in this area, right? So we are thinking, okay, so we have AMD impacted soil and water in hand, so we have to come up with some innovative technology. It should be green, not very costly, because maintenance cost we need to keep it in very minimum. So that was our objective. So what we started, because Dr. Sarkar's group was working on WTRs, is water treatment residuals. I know so many of you have already heard about WTR from me. Let's see what WTR actually is. So it's a drinking byproduct of drinking water treatment plant. So in drinking water treatment plant, they use alum. Based on what type of alum they're using for coagulating or flocculating agent, we can have aluminium, iron, or calcium WTR. For them, it's a waste for drinking water treatment facilities, because what they do, they store them in lagoons. When the lagoons are filled up, they dredge it and send them for land disposal. So every day 2 megaton of WTRs are being generated all over the US, and it's is being sent to landfill sites. But what researchers have found, that WTRs are very good adsorbing materials. So they can absorb metals on their surface because of their presence of iron and aluminum hydroxides and amorphous hydroxide and oxide. So they are like kind of sponge for some metals. They can adsorb. So it could be a good resource for metal adsorption. So we are using a waste to give it a second life. So it's kind of a that's why we are calling it a green. So this is a typical drinking water treatment facility looks like. So you have your treatment facilities here. Then once you are done, you are storing those alums, the WTRs in these lagoons until it filled up. Then you call the dredging guys. They will dredge and bring it to land disposal site. And once we approach them, they're very happy to give it us for free, because for them it's waste. So you can go there and collect as much as possible. Only cost is transportation. That's why we always prefer to use WTR from the drinking water treatment sites, which are very adjacent to your study area. So this was the city of Carbondale, drinking water treatment plant. So we used two types of WTR because we know that the water and soil is very acidic, so we need some kind of neutralizing liming agent. So we used calcium WTR collected from Saline Valley Water Treatment Plant and LWTR from City of Carbondale Water Treatment Plant. So as you can see, CaWTR was highly alkaline, so it is perfect product for lime as a liming agent, and both of them has high amount of both of them has high amount of oxalate extractable iron and aluminium in them. What does that mean? That means it has adsorbing sites for metals. More amount of oxalate extractable iron and aluminium means more adsorbing sites. So it was perfect for us for use. So it was cost effective, as I told. It's free. Just go there, pay for the transportation, and it's all yours. And it's a sink of metals around organics, and it's very non-hazardous because we run TCLIP test. It's called Toxicity Characteristic Leaching Protocol. So what it does, it mimics the landfill condition. So if you send the WTRs for landfill, let's see if it's releasing any toxic metals, because it can be a harmful, potential harmful substances. But both of our WTR came very clean. All the prescribed limit for US EPA was well below under the limits. So both of them can be safely land applied before and after use. So then we selected another remediation agent because, as I told you, another problem with AMD impact is soil erosion. We need something to stabilize the soil. So this is vetiver grass. You saw vetiver grass growing just beside Nicole, right? So let's see what advantages they have. So the first advantage is that they possess a very long and massive root system. It can go up to 3 to 4 meter deep in the ground, and it is a very fast growing perennial grass, and it's non-invasive, and it's a very well known metal hyperaccumulator plant, and it can sustain a different array of environmental harsh extreme condition, and it is very tolerant to fire, flood, and different type of external factors. So you can see it can tolerate very low to very high pH range, and it can tolerate very high amount of metal load present in the system. So and vetiver is very popular for application like mine rehabilitation, slope stabilization, wind barriers. So we thought, okay, let's use vetiver for our systems too. So first we started with removal of AMD, remediation of water, AMD impacted water. So for any kind of study, you have to start with screening test, right, if your method is going to work or not. So what we started doing, we collected water from Tapsilco, and we mixed them with both our WTRs, aluminium and calcium, plus we used both of them the mixture, because individually, so solid solution ratio, the low solid solution ratio means you have to use more amount of WTR. High means you have to use less. So we selected a big range from 1 to 10 to 1 to 150, and we started doing the lab scale study. So what we found, that once we are using only WTRs, like either aluminum or calcium, like obviously calcium bring the pH way above the the initial range. But once we are using both of them together, you can use very small amount of like high solid solution ratio, but it will still give you the same result. So you see the pH almost was near neutral. So we use like 1 to 100 or 1 to 150 ratio, but we can still use, just trying to bring the pointer. Okay, now I got it. All right. So you can see the very high amount of solid solution ratio with both WTR together can give us the result. And then we started checking the metal concentration, what is happening with the existing metal. So 137 ppm of iron. So we saw that with our treatment, it came well below the USEPA range, so 1 ppm. So we know that technology is working. The same thing happened with lead and other metals. So then we started doing the metal adsorption. How fast is the reaction happening? And we found out for most of the metal it was less than 3 minutes. If you do the shaking within 3 minutes, you will get the saturation curve. So in any kind of adsorption, you have to make sure whatever is binding there, it can be come out. It can come out or not. So we did the desorption, and we found that whatever metal adsorbed on WTR surface, less than 3% was coming out for over 48 hours of desorption study. So that means it's irreversible. So that's perfect for our type. We don't want them to bind in the WTR and then again coming out. So it was not happening. So it was very good result that we are getting at that point. So then we started going for the lab scale filter designing. So you have to see that if it is going to work or not. So one disadvantage with WTRs are they are very impermeable for water. If you use only WTR, it's not going to allow water to pass through. So we mix them with sand in different ratios, and before doing any analysis with AMD, we have to make sure which ratio is best for hydraulic condition. So we choose a different type of sand WTR ratio and did a number of hydraulic performances, and we found out 1 to 6 sand to WTR ratio, WTR to sand ratio is perfect for our type of hydraulic condition that we are looking for. So then we started passing our AMD water through that column. So our bed volume was around 53 ml, 10 centimeter, and we constantly pass AMD water through it for 24 hours. And you can see these are the rust trapped inside the bed. You can see with a clear PVC column. You can see it. That means iron is being trapped and taken out from the water. And you can also see it from the picture. It was AMD water before, and this is after. So it's clear. So whatever was there was being removed. The pH was getting high by the treatment. So 2.27 pH was becoming like over 6 for certain time. Remember, this was a very small column, so it can sustain only 20 bed volume, but what we were looking for was there. It can increase the pH and it can take out the metals. So more than 95% of whatever metal was present in that empty water was being removed by this system. So we know that it was working. So it was time to go for the field scale designing of the WTR, keeping the condition in mind of Tapsimco. So we prepared this 55 gallon drum filter. What we did, we packed this filter with like 90 kilogram of our filter media. First, we are using like 1 to 6 sand WTR ratio and 1 to 1 aluminum calcium WTR in that WTR mix. And we first place the, because this is the drum and this is the, outlet. It has a filter coating in it, so you will only get water out. All the WTR and sand are going to be trapped. And any kind of filter, you have to first saturate it with water. And then once we are done that, we pass AMD water, 100 gallon AMD water collected from Tapsimco through the filter. And you can see it's coming out of that, the outlet. The one problem with this filter was the outlet flow was very, it was not up to the mark. It was 1 gallon per minute. We were looking for something like 3 to 4 gallon because of the similarity of the actual size. So what we did, we placed some granulated activated carbon because we were thinking maybe the filter was getting clogged by our sand WTR mixture. So we placed some gap at the bottom and then put the same mixture ratio of sand WTR on top of it. And now see what is becoming 4 gallon per minute. So it was what we were looking for. And you see the difference between the before and after picture, and that was the color. So just by looking it, you know that something is good is happening, because it is a before and after treatment. So let's see the chemical characterization. So the pH became more than 7 from 2.2. The iron well below USEPL limit of 1 ppm. So almost 99, more than 99% iron removal was happening, during that process. And all the metals in those were way above USEPL limit become, almost gone. So more than 100% removal. So once we are done with this, that was the phase 1 study. So what we are looking for, we are for installing this filter in actual lab site. So this is our phase 2 so we are ready. So what the actual field site looks like, so this was the SRB pond, and this is the holding basin. So they are elevated. So once what we can do, we can fit our filter in between this. So there is a already existing pipes, underground pipes to connect SRB water to holding pond. So we can just plug our filter in there and it will be gravity flow. So you don't have to invest any external energy, and it's going to pass through the filter, and it's going to, and that's why the flow rate was important, because 3 to 4 gallon per minute flow rate is happening in that area. So this is, we can easily add our filter there and get the removal. So that was all from the water perspective. Now see what happening with soil, because we don't have to, we cannot forget that the soil is also being impacted heavily for AMD in that site. So we started soil incubation studies. So because we have to see that if it is still working with soil or not. So we mix our WTR product with AMD soil collected from TAPSIMCO in 3 different ratios. These are the typical WTR application rates, 2.55% and 10% weight by weight. And we used AL and CA WTR in 1:1 ratio for another treatment, just to see only LWTR is enough or we need both of them together. So we did this study for 2 months. So what we saw, with presence of both aluminum and calcium WTR, soil pH increased and become almost near neutral. So we know for pH wise it was working. Once you have a total amount of metal, once you analyze your soil and got 137 ppm of iron, but you have to make sure that in what form that iron present in the soil, because that is going to tell you how much impact they can have on the biological system. So in soil, a metal can reside in 6 forms. The most concerning ones for us, for living organisms, are soluble and exchangeable, because they are bioavailable. More soluble and exchangeable form of metal means more harm they can do on biological organism, and all the rest are very strong bonding. So if it is there, it might not impact you that much. So in our soil, what we saw initially, it has very high amount of exchangeable and soluble forms. Once we started our treatment, what we saw within 1 month and 2 months, those two are getting decreased. If you see the compare between control and our treatment soils, exchangeable and soluble parts are getting reduced, because WTRs, they are getting absorbed, and they are also readily available for absorption. Whatever is bound in other forms, they are very hard to extract out. So our goal was to decrease the amount of soluble and exchangeable fraction at first. So, and that was happening. So within 60 days, almost 85% of soluble and 93% of soluble and 85% of exchangeable portion of iron reduced. So that means they were getting absorbed on WTR surfaces. So then we went ahead and did our greenhouse study. In this study, we used PVC pipes. So what these pipes, Here you can mimic the soil system. You can place place some gravels and on top of some sand, and then place your like filled soil on top of it and apply your treatments, and you can grow plants. And once you irrigate the columns, you can collect water, leachate water, to see how much metal is being leached out, so that can reach groundwater. So it's kind of mimicking the whole soil system. So we started with that. So we take 5 and 10% weight by weight WTRs and mixed with 1 by 1 among them, and did this study for like almost 3 months. So first 1 month was soil WTR equilibrium period. You have to give some time for WTR to work, and then we plant vetiver on top of it, and we also selected fescue as a control grass. So, and we continuously collected the leachate water to see what's happening. Turbidity and TSS are the two indicator of soil erosion. More turbidity and TSS in your system means more soils are being washed out. And for AMD, it was high erosion prone. So what you can see with our 5 and 10% WTR and vetiver system, not only pH is getting higher, getting improved, the turbidity and TSS overall were being reduced. So the erosion potential of the soil was getting decreased because of our treatment. So we know that our both removal and and erosion were happening with this kind of treatment. And what we saw, so in our because we analyzed for metal our both vetiver root and shoot, and we saw the translocation factor was less than 0.1. What translocation factor tells you? How much metal the plant is taking up from the soil is being transported from root to shoot. So that's the translocation factor tells you, and you saw the most of the iron were being trapped into the root zone. So once we saw the greenhouse study was successful, and it was giving us a good result in both soil quality improvement wise, we went ahead and set up our simulated field study. So what we did on open air, we established some wooden platform. So you can see it's on a slope. So once the water is coming into, it can you will have both surface water runoff. We have the collection system here, and there are some leachate collection system. So you can both have leachate and surface water over time. So we have here the control with no treatment, and we have vetiver grass on top of a 10%, 5% WTR application. So the same thing we did soil WTR equilibration period, and then we planted vetiver, and we monitored the soil quality over time, and we collected both leachate and surface runoff, because it keep on getting enough amount of precipitation. So every time you get a good number of precipitation, you will go there and collect both surface runoff and leachate. So this is what the plants looks like after 3 months. So plants were happy, because as I told you earlier, vetiver is very resistant plant. It does not need very high amount of care. Just have to plant them there and they will grow. And as they are not invasive, they don't produce any seed or stolons. So wherever you are going to put there, they are going to stay there and keep on growing. You just need to chop it off the shoot, and it will keep on growing until the root freezes. It cannot tolerate cold, extreme cold weather. That's the only negative you can say the limitation of vetiver. So what we saw, the vetivers were highly adaptive of the Tap-Simcoe AMD condition, and they were keep on growing. And what the result showed us, the pH of the both leachate and runoff, as you can see before and after treatment, because this is control panel leachate. Day 3 still remain in the high acidic condition, but when you are talking about the treatment, it way above the acidic range. So it was neutral, or it was being improved dramatically. And the turbidity and TSS, it was getting decreased over time. If you compare the turbidity of control with our treatment, it was more than 98% reduction, and same as the TSS. So we know the both vetiver and WTR system was giving stability to soil. And if you see the metal concentration in both leachate and surface water, you see the concentration which was way higher in control, where almost negligible for arsenic and aluminium, and iron was almost 85% lesser than what we are getting for the control. So it was taking up metal as much as it can. And why we keep on analyzing aluminium? Because we are adding aluminium WTR. We wanted to make sure we are not introducing any extra aluminium into the system. But from this study, you can see that it was perfectly okay and well under the limit. So what we plan to do next on site, so we can apply our WTR in the kill zone, give it some time for equilibration, and then we can plan vetiver. So it will give both stability and from erosion prevention, and will take up whatever metals is being impacted in the system. So with that, these are all the major findings we have. We saw that our filter media is working in the simulated field site condition, so we can install them on site, and both our soil system with WTR and vetiver, they are also reducing erosion potential, improving soil quality by improving both pH and metal concentration decreasing. So with that, this study was funded by US OSM. Dr. Sarkar was the PI of the project, so I was very fortunate to work under this, and I got the scholarship from American Society of Mining and Reclamation that helped the last phase of the study. And with that, thank you so much for your attention, and if you have any question, I would like to take it.